To predict the product of electrophilic aromatic substitution, we need to consider any substituents already present on a benzene ring. In this case, we have isopropyl substituent on benzene ring, isopropyl being an alkyl or R group. R group directs subsequent substituents to ortho and para positions. Let's take a look. Now, the ortho positions in this case are effectively blocked by steric effects of the large group that is free to rotate about the sigma bond. Whenever you have a branched carbon atom, tertiary or quaternary carbon atom at the benzylic position, free sigma rotation about this bond causes the ortho positions to be sterically hindered by other R groups present at benzylic position. Therefore, the electrophile has a difficulty getting into the proximity of the benzylic groups. In this case, the substituent will be directed to the para position. So para substitution will be the major product. Next, let's take a look at what kind of reaction we have here. Since we have an acyl group, we have a carbonyl with the chlorine attached to it. Acyl group, in the presence of aluminum chloride catalyst, affects an acylation reaction. Effectively will transfer the ketone group, since chloride will be expelled, to the para position. So let's go ahead and number the carbon atoms of the electrophile. 1, 2, 3. Our product will be benzene ring with isopropyl group, and then the 3 carbon atom chain, 1, 2, 3, with a carbonyl at the benzylic position transferred to the para carbon. This is an acetophenone derivative, and in the subsequent reaction, we'll reduce this ketone using catalytic hydrogenation. We'll reduce this ketone to an alkane. Hydrogenation over palladium and carbon catalyst system in alcoholic solvent will reduce any double bond outside of the benzene ring or a ketone. It will not reduce the double bond inside the benzene ring. Benzene is too stable to undergo catalytic hydrogenation using hydrogen, palladium, and carbon. We would need much stronger catalyst for this. Therefore, the product will be propyl chain coming from the catalytic hydrogenation or reduction of the ketone. Product, therefore, is benzene. Isopropyl group remains unchanged, and propyl at the para position. 1, 2, 3. Reduction because we increase the number of carbon-hydrogen bonds. We had gone from no hydrogen atoms at the benzylic carbon to 2 hydrogen atoms at the benzylic position. Next reaction is benzylic bromination under free radical conditions. N-bromosuccinimide serves as an in situ source of diluted bromine radicals or bromine atoms, and since we have UV light, H nu, this is a free radical benzylic bromination. Product, therefore, will be benzylic alkyl bromide. Let's look at our precursor B and find the most highly substituted benzylic carbon atom. If that carbon has a hydrogen present, that hydrogen will be selectively replaced by the bromine atom. On carbon number 1, I have 2 secondary benzylic hydrogen atoms, and on the isopropyl substituent, I have 1 tertiary hydrogen. Since NBS and bromosuccinimide is selective for the more highly substituted benzylic and allylic position, this is the hydrogen atom that will be selectively replaced with bromine atom during benzylic bromination. Therefore, the product will be tertiary benzylic alkyl bromide. Benzene, propyl group, and tertiary benzylic alkyl bromide. Next reaction is elimination. Elimination of HBr. Bromine group as the leaving group will be expelled. And now let's find the most acidic hydrogen at the alpha carbon. Here is the carbon atom in question that is connected to alkyl halide. And then let's look for acidic hydrogens which would be present at the alpha carbons. I have 3 alpha carbons. One over here, which has no hydrogen atoms to be eliminated, and even if it did, they are not acidic. And I have 6 equivalent primary alpha carbons. One of those hydrogens will be eliminated by the base hydroxide, affecting formation of the double bond of the pi bond at benzylic position. One of the lone pairs of electrons on hydroxide will grab the hydrogen atom. The sigma bond between carbon and hydrogen will give its 2 electrons to the incipient pi bond, which will form between benzylic carbon and carbon over here, and bromide will be expelled. So elimination of HBr will give us a styrene derivative. Styrene is a compound that is a benzene ring with a double bond in benzylic position. And if we have other groups attached to it, alkyl groups, we'll just refer to it as a styrene derivative. The table of directing effects will find the alkyl group. Our groups, alkyl groups, are right here. We confirm that alkyl group is an activating substituent that directs substitution to para and ortho positions.